Good afternoon, everyone, and a very warm welcome to today's live webinar on Trust Your Data Mastering MSA with LiveQC Tools. We are delighted to have you all with us today and sincerely thank you for taking the time to be a part of this session. I'm Santoshi and I'll be the host for today's webinar. A few housekeeping updates. All participants' microphones are muted and cameras turned off to maintain proper bandwidth. If you have any questions or clarifications, please feel free to post them in the chat box. We'll also have a dedicated Q&A session at the end where we'll address all the questions. Thank you for your understanding, and now let's get started. In today's manufacturing and quality-driven environment, data drives every critical decision from process control to product acceptance. But the key question is, can we truly trust the data we rely on? This is where MSA plays a vital role. MSA helps organizations evaluate whether their measurement systems are accurate, repeatable, reproducible, and reliable for confident decision making. When measurement systems are not capable, even well-controlled process can appear unstable, which may also lead to incorrect conclusion, rework, and avoidable cost. In simple terms, if the measurement system is weak, the data cannot be trusted. And if the data cannot be trusted, decisions become risky. Since 1993, EGS has been delivering engineering excellence and digital solutions to manufacturing industries across India and beyond. For more than 3 decades, EGS has partnered with organizations across diverse sectors, helping them solve complex engineering and quality challenges. Built on this strong foundation, LabQC Tools has been developed by a team of experts with deep hands-on experience in implementing world-class quality and statistical methodology. LabQC Tools is designed to be simple, easy to use, and affordable, and this enables organizations to strengthen the 3 pillars of operational excellence: cost, time, and quality. To provide best-in-class tools and technologies for a better tomorrow is our mission, and that is clear. While many organizations prefer MSA studies, manual execution often becomes time-consuming, inconsistent, and difficult to track. With LiveQC tools, the complete MSA workflow is digitalized, enabling teams to improve confidence in quality data and make faster fact-based decisions. LiveQC tools help organizations trust their data and act on it with confidence. With this context, today's session will focus on how organizations can master MSA practically and build strong, reliable measurement system using LiveQC tools. Now, it gives me a great pleasure to introduce our speaker, Mr. Christopher, who will take us through a practical and insightful session on mastering MSA using LiveQC tools. Over to you, sir.
Hello team. Hope everybody is doing good and had your lunch. Thanks for the wonderful introduction, Mr. Santoshi, and I thank everyone here for your valuable time. This is Christopher, application engineer for LiveQC tools from Team EGS India. We all know EGS India, an engineering solutions organizations with 4 decades of market experiences across CAE, PLM, academics, LiveQC, and so on. Before getting into this topic, let me start with a simple question. How confident are you in the data you rely on every single day? We all know how significant the accuracy of the data that we rely on. Either it is through systematic data or any machine provided man intervened data. From here, let me walk you through how LiveQC helps in bringing accuracy and advancement of the data that we rely on. This brings us for today's topic, trust your data, mastering MSA through LiveQC tools. In this webinar, we will begin with a brief overview of MSA and its significance, the key components of MSA including its study types, and discuss the practical applications of MSA in manufacturing and quality control environments, followed by its aspects and impact. Ultimately, we will connect MSA to problem solving and demonstrate how LiveQC tools improves data integrity and supports decision making. Now, with the given objectives, let's move with our today's agenda. MSA. As we all know, it is for accuracy, precision, and reliability of the measurement system despite the area of deployment. Now, let us now focus on its core purpose, which are dealing with measurement errors, data variation, both in process and system, then improve data-driven decisions and quality standards assurance. It is important to recognize why MSA is so critical across industries, bringing the topmost importance in fields such as validating data integrity and forming a reliable foundation with trustworthy data. Robust MSA supports both audits and regulatory expectations, which also enhances statistical confidence, strengthens the effectiveness of statistical tools such as ANOVA, and then regression analysis, helping with continuous improvement in achieving long-term excellence. Looking here, these are all the common study types, starting from gauge R&R, bias study, linearity study, stability study, and attribute agreement analysis. Let us take a closer look at two critical study types, gauge R&R and stability study. This study is typically performed using average and range methods or ANOVA-based approaches, both of which provide insight into repeatability, reproducibility, and overall measurement system variation. Along with the stability studies are conducted to monitor the consistency of measurement performance over time. Followed by that, let's focus on the accuracy related and attribute based studies. This study is bias in determining whether a system consistently estimates the actual value. Linearity study extends this concept by monitoring bias across the entire operating range of measurements. Attribute agreement analysis, which is used to evaluate the consistency and accuracy of categorical decisions made by multiple appraisers. The real significance of MSA lies not in the studies themselves, but in the questions they help us answer about our systems. At its core, it answers the accuracy of systems, precision of data, stability over time, and consistency of data. Now, let us see some of the key benefits, starting from reduction in variation, reliability in data, risk mitigation, sustenance of audit standards, cost reduction with increased quality outcomes. The core deployments areas of MSA, such as the incoming material inspection, where MSA assures the vendors with the quality of product supplied and its compliance of standards, the wide application of process quality control and exit inspection by MSA is to monitor critical dimensions and tolerances like shafts, bearing, and any other in-house materials that is produced. In laboratory testing, where in MSA validates the precision of equipments used. MSA plays a critical role in automated measurement systems like drift checks, CMM operations, Poka-yoke data captures, torque wrench monitoring include gauge R&R evaluations. Having seen how MSA is applied across incoming, in-process, final inspection, and automated measurement systems, let us now dive deeper into one specific application, the use of height gauges in automated measurement environments. Just imagine a production line measuring a critical component dimension with a tolerance of plus or minus 0.05 mm. The height gauge is used during in-process inspection to ensure the dimension stays within limits. At first glance, measurements appear acceptable, but variation starts to show up in downstream inspection. This is where we break the problem down using ANOVA-based gauge R&R. The first aspect is the operational aspect, the act of measuring the component using the height gauge. If the measurement itself is consistent, then the impact is immediate. Parts may pass inspection on one shift and fail on another. This directly affects product quality, customer satisfaction, scrap rates, and downstream process performance. ANOVA then reveals repeatability variation. Variation coming from the gauge itself. For example, the same operator measures the same part 3 times and gets 10.02 mm, 10.04 mm, and 10.01 mm. The inconsistency leads to unstable in-process inspection response, increasing internal rework and scrap. Next, ANOVA highlights reproducibility variation, which comes from differences between operators. One operator consistently measures closer to nominal, while another measures closer to the tolerance edge. This operator dependent behavior introduces bias, which leads to misinterpretation of tolerance limits and incorrect accept or reject decisions. Another critical aspect is human error. Improper to the next process or even to the customer. Using an ANOVA-based gauge R&R analysis, we can quantify these sources of variation. For an instance, 40% from the gauge, 35% from the operators, and 25% from interaction effects, clearly identifying where corrective actions are required. This level of quantitative insight allows organizations to move from observation to targeted data-driven improvements, which naturally leads us to structured problem-solving approaches. Now, let's look at what happens when measurement system issues are not addressed. Now, imagine a critical component measured close to the upper tolerance limit due to measurement variation. A good part is incorrectly rejected, increasing scrap. At the same time, a borderline bad part is incorrectly accepted, silently moving forward in the process. This measurement error doesn't stop there. When we calculate CP and CPK, the variation from the measurement system inflates the numbers, making the process appear either more capable or less capable than it truly is. Decisions based on these distorted values lead to wrong conclusion. The same error flows into SPC control charts, where false alarms or missed signals occur. Operators may adjust a stable process or worse, or ignore a real shift. Based on this misleading data, teams perform incorrect tooling corrections, chasing a problem that does not actually exist. Ultimately, these issues can escalate into live rejections, customer complaints, and loss of trust, impacting both quality performance and business reputation. Let's now look at how teams arrive at a reliable solution when evaluating height gauge measurement systems. Consider a scenario where multiple operators measure the same component using a height gauge. Even though the gauge is calibrated, the result shows unexpected variation. At this point, a basic gauge R&R method provides limited insight. It tells us there is a variation, but not why it exists. This is where the ANOVA-based gauge R&R method becomes essential. Height gauge measurements are influenced by factors such as probe contact pressure, positioning on the surface plate, and operator handling differences. These influences are not always linear and cannot be accurately separated using simpler methods. Now, ANOVA helps us to statistically isolate and quantify variation from the gauge, the operator, and their interaction without assuming a linear behavior. Because height gauges are highly sensitive instruments, even a small differences in handling can significantly impact the results. ANOVA detects these effects clearly, enabling teams to focus on the true sources of variation. As a result, decisions are no longer based on assumptions, but on measured evidence, making ANOVA gauge R&R the preferred method for the height gauge studies. Now let me walk you through a realistic scenario from the shop floor to illustrate why height gauge R&R results sometimes fail to meet expectations. Imagine a team performing a gauge R&R study on a critical component using a height gauge. On paper, everything looks correct. Trained operators, calibrated equipment, and defined procedures. Yet the GRR results come back higher than the expected. When the team looks closer, the first issue they notice is the surface finish variation. Some parts have minor burrs or uneven finishes. Each time the probe touches the surface, it feeds slightly differently, causing readings to fluctuate by 0.02 or 0.03 mm even for the same operator. Next, they observe parallax errors on the manual gauge. One operator reads 50 mm while another reads 50.02 mm on the same part, simply because their angle of viewing is different. Individually, these differences seem small, but statistically they add up. As the study continues, operator handling differences become apparent. One operator applies more probe pressure, may another aligns the part differently on the surface plate. This shows up clearly as reproducibility variation, not because the operators are careless, but because the method is not fully standardized. Then comes the more subtle issue, insufficient part variation. All selected parts are very close to nominal. As a result, measurement variation appears large compared to part-to-part variation, making the system look worse than it actually is. Finally, the team discovers a slightly one-stylus tip and an improper zero setting of about 0.01 mm. Small issues, but enough to shift every measurement and compromise traceability. In this demonstration, you will see how LiveQC guides the user through a structured and standardized workflow, minimizing manual effort and interpretation errors. The process begins by defining the steady parameters. Here, we specify the measurement types as a variable data, select ANOVA gauge R&R, and identify the measuring instrument. In this case, a height gauge. We then define the number of parts, operators, and trials, ensuring sufficient part variation to represent the process accurately. As shown here, LiveQC captures measurement data in a structured and traceable format, recording operator details, timestamps, and instrument references, which ensures consistency and audit readiness. Once data collection is complete, LiveQC automatically performs the ANOVA-based analysis, separating variation into repeatability, reproducibility, operator effects, part-to-part variation, and even interaction effects are also being analyzed without assuming a linear behavior. The results are displayed clearly, showing percentage GRR, variation contributions, and LiveQC highlights whether the measurement system is acceptable, marginal, or unacceptable based on the industry accepted thresholds. This allows to quickly identify whether the dominant source of variation is a gauge, the operator, or their interaction. Finally, LiveQC generates the standardized gauge R&R report, including charts and conclusion. From that, these reports are ready for audits, customer reviews, and internal quality documentation, eliminating the need for manual report preparation. This demonstration shows how LiveQC not only simplifies the execution of ANOVA gauge R&R studies, but also ensures consistency, traceability, and reliability in measurement system analysis. Along with the ANOVA gauge R&R demonstration, you will now see a workflow videos for bias and stability studies, which follow a similar structured approach in LiveQC. In the bias study, LiveQC compares observed measurements against a known reference value to quantify systematic error. This workflow ensures the consistent data capture, automatic bias calculation, and clear acceptance criteria, helping to determine whether the measurement system consistently over or under the measures. Then the stability study focuses on measurement performance over time. IQC tracks repeated measurements at defined intervals and visually highlights any drift, ensuring the measurement system remains stable under real production conditions. In addition to this, LiveQC also supports a full range of MSA studies. Starting from linearity studies can be conducted to evaluate how bias behaves across the entire measurement range. For qualitative inspections, attribute gauge studies assess the appraiser consistency and accuracy using agreement and kappa statistics. LiveQC also enables multiple gauge R&R study types, including tolerance-based GRR, total variation GRR, and the average and range method, allowing organizations to select the perfect fit their measurement system and compliance. Across all these studies, the key advantage of the LiveQC is a standardized workflow, automated analysis, and audit-ready reporting, ensuring consistency, reliability, and confidence in a measurement system evaluation. After seeing how LiveQC supports advanced MSA studies, let us step back and compare traditional quality assurance approach with the digital quality control platform. In a traditional QA environment, inspection is largely manual and reactive, in which we were relying on checklists and paper-based logs. Data is often limited and static, making it difficult to respond quickly to quality issues. Collaboration in this model tends to be siloed, with quality, production, and engineering operating independently. The primary focus is defect detection, and compliance is maintained through manual audits, which are time consuming and labor intensive. In contrast, a digital QC platform like LiveQC enables automated and predictive inspection. It leverages IoT, cloud-based QMS, and analytics to capture a real-time centralized data. This allows integrated cross-functional collaboration and then shifting the focus from defect detection to prevention and increasing the business value. Compliance is supported through automated traceability and overall efficiency improves through high-speed data-driven decision making. This shift from traditional QA to digital QC is what enables next generation quality assurance, where data is not just collected, but actively used to prevent issues and improve performance. Quality control is no longer just about monitoring. It is about anticipating and acting early. Building on this shift, LiveQC delivers instant insights with zero guesswork. It transforms quality from a reactive inspection to preventive control, reducing defects before they impact production. Like you see, then enables automated data capture and testing supported by a fully integrated cloud-based QMS that provides real-time visibility across operations. By adopting a shift-left approach, quality is embedded from day one rather than inspected at the end. This drives the transition from quality assurance to business assurance, where decisions are data-driven instead of intuition-based. Built-in compliance, traceability, and risk mitigation, along with shared dashboard, enable strong cross-functional collaboration and faster decision-making. As we have come to the summary, today we explored the critical role of measurement system analysis in ensuring data integrity. We began with the fundamentals of MSA, in which we were covering repeatability, reproducibility, bias, stability, linearity, and attribute agreement studies, and discussed their practical impact on manufacturing quality. We saw how ANOVA-based gauge R&R provides deeper statistical insight, separating operator, instrument, and interaction variations to ensure your measurement system is truly capable. Common challenges like operator handling, surface finishing, and part inconsistency can distort results. But like you see, standardized workflows captures data automatically and generates actionable reports, making complex analysis simple and reliable. Beyond measurement studies, like you see, digitally transforms quality operations, shifting from a reactive inspection to preventive control, embedding quality from day one, enabling cross-functional collaboration, and driving data-driven decisions instead of intuition-based QA. Additionally, in essence, when your measurement system is trusted, the decision it informs are reliable, compliant, and aligned with the business goals. As we conclude, and this brings us to the core message. When you trust your measurement system, you can trust every decision built on the data. Every confident decision starts with the reliable data. By mastering your measurement system and leveraging tools like LiveQC, you ensure that your quality processes are not just compliant, but preventive, actionable, and truly business driven. When your measurements are trustworthy, your decisions and your results will be too. Thank you. From here, our marketing expert Santoshi will take over.